In this lesson, we are going to look at the principle of operation of the pressure altimeter and how the pressure altimeter is calibrated. We will also look at the simple altimeter, the sensitive altimeter, and the servo-assisted altimeter. The pressure altimeter can be thought of as a pressure gauge, which senses change in static air pressure, and by means of calibration, expresses the change of static air pressure as a change in altitude. So in order to appreciate how the altimeter works, we first have to look at the atmosphere and how altitude affects static air pressure. In the atmosphere which surrounds the Earth, the static air pressure experienced at any point will depend on the weight of the air above that point. If we imagine a column of air extending vertically upwards from the Earth's surface to the outer limits of the atmosphere, it will be clear that the higher up the column we climb, the shorter the column of air above us becomes, and so the weight of air above us reduces. In other words, the greater the height, the lower the pressure. By measuring pressure, the altimeter measures height or altitude. Unfortunately, the relationship between pressure and altitude is not linear. Additionally, high and low pressure weather systems can produce significant air pressure changes for any given altitude. If we look at the isobar chart shown here, we can see that if we were to travel from the UK to Iceland at mean sea level, the air pressure above us will change from around 1036 millibars or hectopascals to approximately 996 millibars or hectopascals. The matter is further complicated because the rate at which temperature changes within the air will vary considerably, and this affects the air pressure also. With all these variables in the atmosphere, calibration of the altimeter is a complex matter, and it is necessary to assume an average or standard atmospheric condition from which to apply any necessary corrections. The atmospheric condition universally adopted as standard is known as the International Standard Atmosphere, or ISA. ISA conditions assume the following. Firstly, that mean sea level pressure is 1013.25 millibars or hectopascals, and the temperature is plus 15 degrees Celsius, while the air density is 1,225 grams per cubic meter. Secondly, that from mean sea level up to 36,090 feet, or 11 kilometers, temperature is assumed to reduce by 1.98 degrees Celsius per 1,000 feet, or 6.5 degrees Celsius per kilometre. Thirdly, that from 36,090 feet, or 11 kilometres, up to 65,617 feet, or 20 kilometres, the temperature is constant at minus 56.5 degrees Celsius. And finally, from 65,617 feet, or 20 kilometres, up to 104,987 feet, or 32 kilometres, temperature increases by 0.3 degrees Celsius per 1,000 feet, or 1 degree Celsius per kilometre. On the basis of these assumptions, the pressure which corresponds to any given altitude in the ISA can be calculated, and under laboratory conditions, any altimeter readout can be checked against the ISA calculated figures. Any discrepancies within accepted limits can be listed as instrument error over the operating range of the altimeter, and can be recorded on a correction table for the altimeter. Before we move on to looking at how the altimeter works, something that will be apparent if we think about it is that if the altimeter is calibrated to ISA conditions, the altimeter can only indicate the correct altitude where ISA conditions exist. And as we have seen, atmospheric conditions vary considerably. The lesson on altimeter pressure settings deals with how we overcome this problem. Let's look at how the altimeter works then. In its simplest form, static pressure is fed into a sealed instrument case from the static source. Inside the instrument case is a partially evacuated capsule, or aneroid capsule. Expansion and contraction of the capsule is kept under control by a leaf spring, and the controlled movement is transmitted via a system of linkages to the pointer on the instrument dial. As altitude increases, the static pressure inside the instrument case decreases. The capsule expands, which causes the pointer to rotate and indicate an increase in altitude. In the descent, the capsule is compressed, and the pointer moves in the opposite direction. The linkage incorporates a temperature compensating device to minimize errors caused by expansion and contraction of the linkage and changes in spring tension due to changes in the temperature of the mechanism. We can see the principle of the linkage mechanism in operation, although the actual arrangement is much more complex. The simple altimeter has a manual setting knob which is geared to the pointer. If this knob is used to set 0 on the ground, we call the altimeter setting QFE, and we say that the altimeter indicates height. These terms will be explained in more detail in the next lesson. If we set the airfield distance above sea level when on the ground, we call the pressure setting QNH, and the altimeter indicates altitude. Again, we'll explain this in more detail later. The sensitive altimeter uses essentially the same principle of operation as the simple altimeter, but incorporates some additional refinements. The single aneroid capsule of the simple altimeter is replaced with a bank of 2 or sometimes 3 aneroid capsules. We can see 2 capsules represented diagrammatically here. The combination of capsules gives increased movement for changes in pressure, and this makes the instrument more sensitive to small changes in altitude. Accuracy is also improved by the use of jeweled bearings in the mechanical linkages, which reduces friction. As with the simple altimeter, a temperature compensating device is incorporated, which minimizes the errors caused by expansion and contraction in the linkages. Some sensitive altimeters incorporate vibrators, which help overcome friction and the inertia of the mechanical linkages. This assists in giving a faster response rate to altitude change. Looking at the sensitive altimeters illustrated on the screen, we can see that the more sophisticated mechanism of the sensitive altimeter enables the use of 3 pointers on the instrument dial. 1 pointer for tens of thousands of feet, 1 for thousands, and 1 for hundreds of feet. While this may initially be seen as advantageous, there is a major shortcoming here, in that the 3-pointer system is easy to misread. Both the altimeters shown here are actually indicating 24,100 feet. If we look at the sensitive altimeter to the far right now, we can see that in this version of the instrument, a much clearer display is achieved by substituting 2 of the 3 pointers with the digital altitude readout. A single pointer is retained to indicate 1,000 feet per revolution, and to provide a valuable indication of the rate of altitude change. This altimeter is also indicating 24,100 feet. Move the aircraft up and down and observe the different indications of altitude. The sensitive altimeter also incorporates a variable subscale, which can be manually controlled to set a required pressure datum. The relevance of this facility is discussed in the lesson on altimeter pressure settings. But let's take this opportunity to see how changing the altimeter subscale changes the indicated altitude. A further refinement of the pressure altimeter is the servo-assisted altimeter, which gives improved accuracy, particularly at high altitudes, where the change in air pressure is much smaller than at low altitudes for a given change in height. The principle of the servo-assisted altimeter is that direct mechanical linkage between the aneroid capsules and the pointer is replaced with an electromagnetic system. Minute movements of the capsules can be sensed by this system, and the movements converted into electrical current by an electromagnetic pickoff. The electric current generated is amplified and used to drive a servo motor which rotates the pointer. We can see here in diagrammatic form how this is achieved. Movement of the capsules is transmitted to a pivoted bar, known as an I-bar. Opposite the I-bar is an E-shaped bar. As we can see, the E-bar has coils wound around each leg. The coils on the outer legs are wound in opposite directions, which causes them to be 180 degrees out of phase with each other. AC current is fed to the middle leg, which sets up an alternating magnetic field in the outer legs. Because the windings on the outer legs are 180 degrees out of phase with each other, when the gap between the I-bar and the legs of the E-bar is equidistant, the magnetic fields generated are equal and opposite and cancel each other out. No current will therefore flow in the circuit. When the capsules expand or contract with changes in altitude, they move the I-bar on its pivot, and the gap between the I-bar and E-bar will change. This causes an imbalance in the magnetic fields, and an electrical current will flow in the circuit. The current is amplified and fed to the servo motor, which drives the pointer. A worm drive and cam mechanism realigns the I-bar with the E-bar. Once realigned, equilibrium is restored, and the altimeter indicates the correct altitude. In practice, the E-bar movement and the realignment can be considered to be a single continuous process. To recap then, we can say that the advantage of the servo-assisted altimeter are that it gives improved accuracy, particularly at higher altitudes. Additional advantages are that friction and manufacturing imperfections in the mechanical gearing of a conventional altimeter are reduced, and altitude sensing in electrical form is available as a central source of information for digital readouts and systems, such as autopilot, flight data recorder, and altitude warnings. This concludes the lesson. A summary of the main points to consider from the lesson follows. The pressure altimeter senses change in static pressure, and by means of calibration expresses the change in static air pressure as a change in altitude. The greater the altitude, the lower the air pressure. High and low pressure weather systems produce air pressure changes at any altitude. An adopted standard atmospheric condition is required in order to calibrate the altimeter. The standard atmospheric pressure is the International Standard Atmosphere, ISA. The pressure altimeter consists of a sealed instrument case with a partially evacuated capsule or aneroid capsule inside. Static pressure is fed to the instrument case. As altitude increases, the static pressure decreases, and the aneroid capsule expands, causing a pointer on the altimeter dial to show an increase in altitude. The converse applies in the descent. The simple altimeter incorporates a manual pressure setting knob and a temperature compensating device in the linkages. The sensitive altimeter incorporates 2 or 3 aneroid capsules to increase sensitivity to small changes in altitude. In the sensitive altimeter, jeweled bearings are incorporated to reduce friction. In the sensitive altimeter, vibrators can be incorporated to overcome friction and the inertia of mechanical linkages. The sensitive altimeter allows the use of a 3-pointer dial. However, it is easy to misread. The servo-assisted altimeter gives more rapid response and improved accuracy, particularly at high altitudes. The servo-assisted altimeter replaces mechanical linkages with an electromagnetic E and I bar system.